Okay, today we're going to talk about this this transformation. This is another transformation where it's a one-to-one mapping from one set of points to another set of points, to a plane to a plane. It's called reflection. This reflection, do you think this reflection is one of the special type called isometry? Yeah. Okay. So you can imagine if you reflect something, maybe on a line or something like that, right? Doesn't it preserve the what must be preserved in order to be an isometry?
The
distance, right? And from the color we know that the angle measure and the area must be preserved also, right? So that's our theorem. Guess what the theorem says? Reflection on a line is an isometry. So write this down. There it is. Okay. So reflection in a line is an isometry. Yeah, very, very easy to remember, and it makes sense, doesn't it? So reflection. So we're going to prove it in a minute. Not fully, but we'll talk about this. But so write this down. I'll wait. Very straightforward. So here's an example of reflection of point P on this line M. Where would P prime be? Well, right on the other side, right? Q on the other side. And S, if S is on this line M, the image of S will be S prime will be the same as S, right? Does that make sense? How would you describe this? Because I said it's on the other side. But if you say on the other side, that's not really. So the way they describe it is, they say the M must be something of the segment P to P prime, Q to Q prime. What must M be? Jordan? Perpendicular bisector. Exactly right. What about the case where the point is on this line? Is that a perpendicular? Is M perpendicular bisector? Can you say that? Is M a perpendicular bisector of a point? Not really. So we don't say that. But if the point is not on this line of reflection, then M must be the perpendicular bisector of these segments. Does that make sense? Yeah. So this is how we define it formally. Here's a reflection. Write this down. So you got to have two cases where the point is on the line or what? On the reflection point line of reflection or not on the line of reflection. So it says this: a reflection in a line M maps every point P to a point P prime such that if P is not on the line M, then M, the line, is the perpendicular bisector of the segment P, P prime, as we said. Okay. And of course, if it's on it, guess what? They're equal, exactly. Very good. If P is on line M, then P prime is equal to P. Very good. So pretty straightforward definition, just as we expected. So write that down. It's a lot more accurate than saying, oh, the point has to be on the other side of the line of reflection, right? That's kind of vague. So you gotta be a little bit more precise, and the way the way they do this is using the perpendicular bisector of the line segment. Okay. All right. So let's talk about what kind of notation we use. So to abbreviate reflection in line M, we use capital R and subscript M. Okay. Of course, the capital R represents the reflection, and M represents the line that is being reflected, right? Because you need both of those information. If you just say something is getting reflected, well, you don't know off of where, right? It doesn't make any sense. And a little more, to abbreviate the statement that here, you should expect, to abbreviate the statement that the reflection in line M maps P to P prime. Rather than writing that whole thing, we just use the mapping notation. And, you're used to this, right? We talked about this yesterday, how we use mapping notation. Instead of equal sign, we use the arrow, and we have colon. And to use function notation, of course, you just use equal sign and then use parentheses, okay? So you should be aware of both ways of representing the statement that reflection in line M maps P to P prime. That's what we use, okay? Pretty straightforward, okay? And you could also read this as P is reflected in line M to P prime. Same thing, okay? So write that down, and you should know how to abbreviate these statements like this, okay? And that they mean the same thing. So let's go back to our theorem. A reflection in line M is an isometry. And of course, with these theorems, the fun part is to prove them. Yeah, when you prove them, it's more. Okay, so how would you go about proving this? Do you think algebraic proof or coordinate geometry proof would be appropriate for this one? Yeah, exactly. So let's think about this. By the way, so let's think about it. So here we go. So if you want to prove that the reflection is an isometry, reflection in line N. Oops. Reflection in. Let me move that. Hold on, give me a sec. Let me move that up here. So to prove that reflection is an isometry, what would you need to do? If we were going to use algebraic proof or coordinate geometry proof, first of all, we need a line to reflect, right? So let's say we have this x and y axis. Which do you think would be a nice line to reflect on? Y axis? I think so. So yeah, let's use the y axis. To do that, we use capital R, and to show that it's, thank you, if it's a y axis, we just write y. That's what that means. Instead of writing the equation of the line, if you just write y, that means we're reflecting this off of the y axis. And let's reflect point x comma y, and what would that be? So let's plot a point. So by the way, in order to show that the mapping is an isometry, what do you need to show? So let's plot this point P. Let's call this point P, by the way. What should we call it? AB or x of 1 comma y sub 1. Can I do that? How come I would use x of 1 y sub 1 instead of AB? I could, but isn't it easier to see which one represents the x coordinate, which one represents the y coordinate? Because if you just write AB, you don't know which one is which. Also, is that all we need? No. We need more than a point to show that the mapping is an isometry. How come? In order to show that the mapping is an isometry, what do we need? 2 points. Because? Yeah, then what does the isometry say that it has to do? It has to preserve the distance. In order to have a distance, right? Don't you need 2 points? So I'm going to call this P. Let's call this point Q right here. Is that okay? Yeah. What should I call this? 2 negative 4? Would that be? Why not? How come I don't want to do like here? I know this is 3 4. How come I don't do 3 4 and 2 negative 4? How come I want to do this as x sub 2 and y sub 2 like this? Yeah, you have to show not a particular distance, but every right? Every segment must have the congruent, right? The distance has to be equal. Does that make sense? The length of the segment, every length of segment has to be equal. That's why if I do this, right, it'll represent every segment you could think of, right? Any length, right? Because this is some arbitrary point. That's why you have to use these variables, right? You can't just do 3 4 and 2 negative 4 and say, oh, if you reflect these points, the distance will be preserved. That doesn't show that it's an isometry, right? It's true for that particular case, but it's not true for every segment. Okay, so where would then P prime be if I did this? So let's just do it with actual points, okay, since it's a little bit easier that way. So if you were to reflect 3 4 off of this line y-axis, right? That's the line of reflection. Where would P prime be? How about Young? What do you think? Where would P prime go to? Negative. Oh, right. So in this case, this is 3 4, right? So what would that be? Yeah, negative 3 4. Wouldn't it go here, P prime? And of course, this will be negative 3 4. And how would you write that in terms of x of 1, y sub 1? You're right, Young. It would be x, instead of x of 1, it would be negative x of 1, comma, y sub 1. Would you not agree? So that's what reflection does if you were to reflect, right, in line y-axis. Where would then Q prime go to? How about Joshua Park? So Q is 2 negative 4, right? Where would 2 negative 4 go if you were to reflect this? Negative 2, negative 4 is exactly right. Wouldn't it go here, guys? Here's Q prime, negative. So instead of writing negative 2, negative 4, I should write what? Negative x of 2 comma. No, is it negative y sub 2? It's just y sub 2. The y stays the same, right? You're just moving it to the others. So what would this mapping be? If you were to reflect, right, a point xy along the line y, the mapping will be what? Basically, negative x comma y, right? In this case, right? If you were to reflect on the y-axis, would you not agree? And of course, we have a segment, right? So if I have a segment, PQ, this segment will get mapped to P prime, Q prime. Isn't that right? Isn't that right? Isn't that how it's going to get reflected? All right. So, am I done proving that this reflection is an isometry? No, I'm just kind of getting myself ready, right? What would you need to show that this is an isometry now? So I have set up my points, right? The segments like this. What do I need? 2 people see it? Okay, go ahead. 3. Go ahead. 4. I want you to talk with your group. Go ahead. What do we need to do next to show this in isometry? How about Brandon? What did your group come up with? What do we need to do next to show that this mapping is an isometry?
We have to connect the.
Okay, let me give you a hint. If mapping is isometry, it must preserve the. Okay, do you know how to? Yeah, you use the distance formula, and which length do we need? Length of?
Q prime and P.
Yeah, that should equal to what? The length of? P and Q. Do you know how to find the length of PQ, guys? Do you know how to find the length of P prime, Q prime? Yeah, we have the order pairs. Go ahead, everybody try, see what you get. I'll wait. So, who could tell me what is the length of PQ? How about Leah? Where did you get the length of PQ as?
Square root of x1 minus x2 squared plus y1 minus y2.
Yeah, I wrote it with x2 first. Does it matter? Okay, same thing, right? Here we go. Does that make sense?
Yeah.
Did you all get that? Okay, good. What about the P prime, Q prime? How about Nico?
What?
The length of the P prime, Q prime?
It's the same thing.
Oh, I didn't guess anything when I. Because what is your x sub 2? It's negative now, right? So don't you get square root of negative x sub 2 minus negative x sub 1?
Yeah, but it's the same.
Oh, really? Okay, so did you get this first?
Yeah.
By the way, I shouldn't put that there, right? Okay. I should just write PQP. Okay, so how is the same thing? They look different. I have negative x, right, look, don't I have negative x squared minus negative x? Isn't that negative x squared plus x1?
Yeah.
They look different.
Once you square it.
That's right. Once you square it, it's the same, right? Because, well, before, yeah. You know, so the rest is the same, but if you look at it, isn't this really negative 1 times x sub 2 minus x sub 1? The whole thing being squared? Well, what's negative 1 squared? 1. And you just get simply x squared, x sub 2 minus x sub 1 whole thing squared, right? Or you could just multiply it out, right? You get trinomial, right? You get the same trinomial. Right? That's another way of seeing it. Does that make sense? So therefore, even though in the very beginning they don't look like they're the same length, they are. Okay? Does that make sense? And now that shows that the reflection, right, is an isometry. Does that make sense, guys? Okay. All right.
Yes.
Okay, Emily, what's your question again?
Could it go to the opposite quadrant?
Very good. So I want you, can you read this for us, Emily? This is what we did. Okay, so
To prove theorem 14.2,
which is this theorem? Reflection in a line is an isometry,
by using coordinates, we assign coordinates in the plane so that the line of reflection becomes the y-axis.
Mm-hmm.
Then in coordinate terms, the reflection is r of x1,
X sub 1, y sub 1.
x of 1, y1,
Maps
map
to.
negative x of 1, y of 1.
Mm-hmm.
In exercise 23 on page 576, the distance formula was used to prove that P equals P prime and Q prime.
And we just did it. It did, right? Okay.
Although the diagram shows P and Q on the same side of the y-axis,
Mhm.
you should realize that the coordinates x of 1 and y of 1, and x of 1, y of 1, x of 2, and y of 2 can be positive, negative, or 0, thereby converting all cases.
Yes, so it covers every cases. So Emily, it could be the P. It does. Yeah, right. It doesn't. Looks like P and PQ has to be on the right side. Does it have to? No, because X sub 1, Y sub 1, X sub 2, Y sub 2 could be any order pair. That's why we use these variables. So does that answer your question? All right, and let me show you something else too. So this is a nice, really, we showed you Desmos graph. If you go to geogebra.org, right, this is actually a really great graphing thing for geometry. So take a look at this, and it's really easy to do. I'll show you when we get a chance. But look at, I'm reflecting AB off of this y-axis, right? And look at my reflection. And let me show you, Emily, when A, if I move it around, it's here. It's reflecting, right? Now, what would happen as I go past each other? It's going to reflect this face still. So yeah, still reflection. Of course, this part on the other side now. Some part on the right side, some part on the other. Do you understand? This is what you're asking. I could actually even move this over this way, right? The whole thing will be on the left side. Does that make sense? So this is really kind of cool program that you could play with. Yeah, geogebra.org. Okay, so you guys should check it out. Does this make sense? So Emily, does that answer your question? I'm glad you asked that because I wanted to show you this anyway. Does that make sense? All right, good. All right. Okay, so right now I have set up so that the line of reflection in the y-axis, right? Also here, what happens if I actually put this point on the y-axis? There'll be the same point, right? Does that make sense? Now, one of you said, well, does the reflection have to be on the y-axis only? Well, not really. Let's see if I can move the. If I were to now, I could do another way so that S could have it reflect on x-axis if I wanted to, or any. Does the reflection have to be on the x and y-axis only? No, it could be any line. So actually, we're gonna do some examples like that in a minute. So very good question. It does not have to be the y-axis, but that's the easiest one to kind of prove it and so forth and show, right? Okay, so the line of reflection does not have to be y-axis. It could be any line if you want. It'll still be isometry. Okay. All right, very good. Let's move on. So it turns out we could actually prove this theorem without using the algebraic proof or coordinate geometry proof. We could just do it using good old two-column proofs, remember? Right? Now, in order to do it, though, if you want to use a two-column proof, you're going to have a bunch of cases. Okay? You're going to actually get 4 cases to think. So if you want to do it that way, first of all, let's read. We have to use the definition of the reflection. Okay, so somebody read this for us. How about Brandon? We'll go ahead. And then we'll get you next check. Go ahead.
Theorem 14.2 can also be proved without the use of coordinates. If coordinates are not used, we must show that PQ equals P prime Q prime for all choices of P and Q. 4 of the possible cases are shown below. In written exercises 18 through 20, you will prove Theorem 14.2 for cases 2 through 4, using the fact that the line of reflection M is the perpendicular bisector of P prime and Q prime.
You guys remember this? That comes from where? The definition of the what? Where does that part come from? That M is the perpendicular bisector of P prime and Q prime. That comes from the
Reflection.
yeah, definition of the reflection, right? So what are the 4 cases? Well, first one is where P, Q, and P prime, Q prime are all collinear, and also Q is on line M. Second case is where they're not collinear, but still one of the point is on the line M. Third case, do they always be on one of the point? Does one of the point has to be on line M? No, it could be off of line M. Guess what the fourth case is? Yeah, if one of them is on the right side and the other point is on the other side of the line of reflection. So which one would you like to prove if you had a choice? Yeah, the coordinate geometry proof, or the algebraic proof, or actually the two-column proofs that we studied. Algebraic would be a lot easier. Does that make sense? This is a classic case where algebraic proof is a lot easier than actually doing this in 4 different cases. It's not that bad. All right, so there we go. Does that make sense? You see how we get 4 cases that you got to do? All right, let's move on. Okay, so since reflection is an isometry, it preserves 3 things. What does it preserve? First of all, it preserves the distance of every segment. Secondly, what? It preserves from the corollaries that we learned. Also the angle measure, and also, lastly, the area, right? You guys remember that? All right, Reagan, can you read this for us?
It preserves the distance, angle measure,
is that the distance, comma angle measure, and the area
Invariant?
under
Huh? What do you think invariant means, guys?
Not changing.
Yeah, it doesn't change. Okay, so another way of saying that the area, the area, distance, and the angle measure doesn't change, right? We use the word invariant. Does that make sense? But turns out, there's one thing actually. So this is great that it's an isometry. What do you think they mean by this? On the other hand, the orientation of a figure is not variant, meaning it changes under, not invariant under reflection because of
Backwards.
yeah, exactly. So, what do you think they mean by this? On the other hand, the orientation of a figure is not variant under reflection,
it is variant.
meaning it changes. What changes? Well, let me give you a hint. Take a look at this picture.
It's like a mirror.
So, what do you think they mean by the orientation in this case? Go ahead, I want you to think as a group. Here's a hint. Think about it. What do you think they mean by this? Alright, so, what do you guys think this means? On the other hand, the orientation of figure is not invariant under a reflection. What do you think they mean by orientation? Who would like to explain this? Jack?
I don't know.
Oh. Oh, really? The hint doesn't help you too much?
Well,
Yeah. What do you think?
the placement,
What do you mean by that?
like.
Well, I think I have an idea. Yeah.
When you have a reflection, you have to like flip it over completely. Not just, it's,
Right. So what do you think they mean by this orientation? And hint, look at the picture on the right. What are they trying to show you here? Yes, Joshua?
The direction of the shape.
What do you mean by that? Yes.
It's like if you have a part on one side, it's on the other side. Like if you have like hands, like, you know, it's like kind of like they're a reflection because the thumb is on the right. Here,
Okay.
and the thumb is on the left. There.
Good. Okay, good. That's the right idea. That's the right idea. Also, what do you think? What do you think they have these arrows on this for? What do you think? Yeah. If our pre-image is going clockwise, will my image going clockwise also? Would it go clockwise also? No, it wouldn't.
The direction is different, Mr. Hall.
Yeah, so that's what they mean by orientation. Watch this. It's not. It's just a very simple idea. Somebody read this for us. Jonathan, can you read this for us? On the other hand.
On the other hand, the orientation of the figure is not invariant under a reflection because the reflection changes a clockwise orientation to a counterclockwise one, as shown at the right.
Does that make sense? Okay, so that's what they mean by the orientation. As you can see, if something was going clockwise, right? If you were to reflect this, would it still go clockwise? No, it will go counterclockwise. Okay? Does that make sense? But do you have to have that going same direction for it to be isometry? Of course not. Only thing that isometry cares is whether every segment preserves the distance, right? It doesn't care about the orientation, but they just want you to understand, right? Just because the length gets preserved, it does not necessarily mean that the orientation will be preserved as well. Okay, does that make sense? So in reflection, the orientation does not get preserved. All right, let's do some examples then. Here we go. Okay, how about, why don't you all try this example? It says, draw the image of the following figure by R sub K. What do you think R sub K mean? Yeah, reflection in line K. Okay, yes, go ahead, everybody try. Now, do you think, knowing the definition, right, the K has to be what? Every time you reflect, K has to be the perpendicular bisector of the pre-image and the image, right? If you were to draw a segment through those. Go ahead, everybody try. I'll wait. How many people got something like this on the left side? Okay, very good. If you look at A prime and A, if you were to draw a segment K, do you see how K is a perpendicular bisector? That's what you do. So if you get C and C prime, as you can see, the K is going to be a perpendicular bisector and so forth. Yes? I like the second one because one of the points is on the other side. Did you get one something like this?
wait, we're supposed to draw it on the.
Yeah, because you're reflecting off of K. So A, you see how A goes to the other side?
Yes.
right? So A prime is right, and then you can see A and A prime is going to be, the K will be line perpendicular bisector. So would the K will be a perpendicular bisector of B and B prime, and so on. Does that make sense? Yes. Now, what if I give you actually order pairs like this? What would you do? Okay. So what do you think? Let's hold on. What do you think R sub X mean? Reflect on x-axis. What do you think R sub Y mean? Reflect on the y-axis. Do you think you could actually kind of graph this if you wanted to? Yeah, go ahead. Everybody think about it. See what you get. Go ahead. I'll wait for you. So when you reflect this, did you get negative 2, 3 for this here? Okay, what about this? Don't you get 2, negative 3 if you were to reflect on the y-axis? Now, what if I ask you to graph? What do you think this means? Y equals negative x. No, what kind of lines do you get? It's a line. What is the y-intercept of this line? Line of reflection, 0. What is the slope? Negative 1. So don't you get something like this? Here's negative 2, 3, and then the A prime will be 2, 3. Does that make sense? Because this red line will be the line of reflection. So line of reflection does not have to be x-axis or the y-axis. Does that make sense? All right, have a good day, guys. Thank you.